with electron microscope. In fact, many more people in the world. There were several groups in the world which played around right inside the electron microscope. We would create atoms of certain materials and then see by evaporation. We do that in the microscope itself, which obviously makes it very dirty. But then, as I said, well, we were taking risks at that time, and we found how the atoms came together. Not atoms, but clusters of atoms, because the resolution of electron microscopes was not very good at those days. So you could see probably tens or hundreds of atoms at one time, and what we call nanomaterials today, we could see them nanomaterials, and then how they run around and how they create atoms. So this is exactly what we did many years ago. Movies were made. We also made a movie. I won't show that today, but this is what so this is the story that I'm going to talk about, and then obviously go on to how far this science and technology of thin films has come to. Okay. So next slide. Okay. So how do we create these species, for example? Okay. There are many ways now. Of course, we are more clever now. We're more intelligent, and we know how to create atoms from materials by variety of techniques like physical vapor deposition or sputter deposition or chemical vapor deposition. We can create ions also. Not only atoms, we can create ions. We can create radicals. And of course, we can create molecules. So there are a variety of these processes available today. Okay. But most important thing to remember, those who work in this field, and they forget, unfortunately, they are used to using the big machines or automatic machines to make materials and thin films, and not realize very fundamental thing. And that's what I want to emphasize, particularly for students who get involved in this area of research. And that is each technique, whatever technique you use, whether it's physical, chemical, or electrochemical, each technique yields unique atomic species. Unique atomic species. Please remember that. So they may be the same number, same atom, but they have different properties, and they have unique characteristics which affects nucleation and growth, and thereby all their properties. That's extremely important to remember here. So each technique has a number of parameters which affect these, and therefore, okay. So this is just to show you what really takes place. And as Maxwell said, well, these atoms are running around, obviously. They have energy. When they hit a surface, they run around on a surface, and they are not happy. They will go back to the vapor phase if they are not stabilized. But if they meet some other atoms, for example, then of course they form a cluster of two, provided they like each other. Provided I made it very clear. As you can see on one side here, they are attracted when they come very close. Of course, they are repelled when they come closer than that. There's a well-defined distance between two atoms at which the attraction is maximum, and below next, if it is lesser than that, they are repelled. And of course, greater than that, they don't attract each other. So two atoms, if they like each other, they become a pair, and then they run around, they attract another atom, they become another pair. So when there are a few of them there, then they decide what structure to take. And that obviously is decided by the forces between them, and the directional forces between them try to minimize energy. So they can make a triangle, they make a tetrahedron, they make a square or rectangular or hexagonal. This is exactly what they do. In fact, we can see many of these things happening inside the microscope, particularly today, when the electron microscopes now literally see atoms or at least few atoms together. Okay. So this is to show you what is the physics behind it. There are two energies that are involved when the atoms come together. There's a surface energy, and the surface energy rises because of the bonds which are unsatisfied. So there's a surface energy which try to sort of break them up, because surface energy doesn't like that way. And the volume energy is the forces between the atoms and clusters or whatever, and that's attractive. So it's a repulsive and attractive forces. It is a combination of the two. And this combination takes over to volume energy that's attractive only when the number of such atoms is a critical size is achieved. So the number could be 10 atoms, could be 20 atoms, could be 100 atoms. It depends on the material. It depends on the temperature at which they are there. It depends on the energy of the atoms that are running around and so on. Okay. So essentially what we see is atomic species. As I said, execute random motion, and they do that. And I already explained that surface energy is proportional to r square, the surface area, and the volume energy is proportional to r cube, and ultimately the r cube takes over, and so on. So this now, of course, we are more or less with the present electron microscope, we can literally see that now at what stage they become attractive and become a solid material, for example. So lateral, in this process, both lateral growth and vertical growth takes place here. But let's remember now, the growth mechanism, there are 2 or 3 types of growth mechanisms that take place. One is directly from vapor to solid. The other is from vapor, it becomes a liquid, and then a solid. Okay. And if liquid is supersaturated, the solute is ejected in the form of nanofibers, wires, platelets. This is exactly what happens. The nanocarbon, for example, we talk so much of the carbon fibers. Okay. So I think one has to remember. So the process is similar. Only thing is the temperature at which we deposit tubes, for example, carbon tubes, for example, that's very high, and it's a very highly supersaturated solution. So the carbon tubes are really created out of a solution. They are ejected from a solution which is supersaturated solution. So the mechanism of forming carbon nanotubes is slightly different from that of, say, from vapor to liquid directly or vapor to solid directly. But in all cases, doesn't matter which route they take, there are parameters that determine the nucleus growth are many. And for example, do you have the atomic species? Are they single? Are they single atoms? Sometimes even molecules come in. What is their flux? How many are there? What is their energy? What is their kinetic energy? What is their angle of deposition? Now that's also extremely important. Angle of deposition, and then what type of ambient do you have? What type of substrate you have? What type of interaction they will have? If the surface is rough, for example, they will not be able to form big clusters, so they'll form naturally more or less a amorphous type of structure. Substrate temperature, the sticking coefficient, surface diffusion, absorption, desorption, and so on. And similarly, critical size will be determined by these. So what I want to say here is that there are at least a dozen parameters which define the whole process of formation of nucleation and growth, and that the young people are never taught that easy. And ideally, and all they are given is a big system, automated system for deposition, and they are very happy to see a film, but they don't understand what has gone beyond that thing, because this is what decides ultimately the properties of thin films. Okay, so changes take place while this process goes on. A lot of changes take place here. You go grain structure, for example, those clusters of atoms that are formed, they could be very small, they could be very large, they could go from nano to micro size, they could be porous, could be dense, could be columnar. You can make columns out of this thing. And the morphology, of course, will be, they could be quantum dots, rods, quantum rods, spinels, films, and multi-layers. The microstructure could change from nano to micro crystalline. They could be oriented. If the substrate is right, the temperature is right, they could be epitaxial also. They could be quasi-crystalline also. So the topography can vary from atomically smooth surface to micron scale roughness here. And the crystal structure depends very much on the interaction between the atoms plus other conditions that prevail on a surface. Okay, so you can change a lot of structures. A lot of structures which are like FCC, face-centered cubic, they can become hexagonal or vice versa. For example, that's quite easy to do that. Okay, so you can make polymorphic structures, for example. So and of course you can make non-equilibrium structures, because at that stage they have no choice but to get together. So you can form alloys and compounds with variable composition, which you cannot form normally, because this is a thermodynamically non-equilibrium situation. You can form A and B, 2 atoms together. It doesn't matter how, they will have to learn to get together, and so they can make an amorphous material, but they will have to. The chemical structure can change drastically. So therefore, in the area of thin films or whatever you want to call them, nanotechnology, nanomaterials, you can make 2-3 materials together, even whether they like each other or not, form a structure which may not be crystalline or may be crystalline, and so on. So obviously, with all these properties changes, physical and chemical properties of the material, they depend obviously strongly on the nucleation and growth process. And that's exactly why I'm emphasizing that should be taught much more carefully. I'm giving an example from my book, of a 1969 book. As you can see here, that I'm talking of angstrom. In our days, we used to call them angstrom. So, 1 angstrom, 10 angstrom is equal to 1 nanometer long today. Okay, and this is just to show you what happens. This is a simple material like gold. We naturally study gold because gold is more simpler material, simplest possible material, doesn't interact with too many things, okay, and doesn't oxidize. And so you can use poor vacuum and so on. So this is just to show you how, whatever I have described, this is how the growth takes place, okay. As the film grows here, the small clusters become bigger and bigger, and there is and then ultimately they combine together. When they combine together, naturally their lattices are different. Their orientation of the lattice is different. So they come together, they form a lot of defects. So thin films normally polycrystalline are very, very highly defective. Well, okay, that has advantage also, mind you. It gives them very strong strength, for example, mechanical strength. For example, gold thin films are 100 to 200 times stronger than gold is, much stronger. And this is very useful for space applications, for example. Okay. So, but this is not the only one. You change the parameters and change the vacuum conditions, deposition conditions, you can change the structure drastically. Like I've shown here, silver you can, if you go slowly, nicely, put the atoms together, or you form silver, single crystal, small droplets in a way, small particles, okay, different shapes. You can see here quite a different shapes here. Or you can form wires if you want, like cadmium telluride, you can wires in it if you want to. Or you can make like a powder, for example, nickel. This is like a powder, fine powder, nanoscale powder. You can make that. If you deposit at an angle, you form long wires, for example. Okay. So, of course, carbon nanotubes, you have heard, this is from a supersaturated solution, comes out nano wires, okay, randomly. Similarly, you can make nice, beautiful flowers if you want, zinc oxide I've shown here. This is just to emphasize that by changing deposition conditions, you can get a variety of structures, very different. So people who work with thin films are generally young people, not taught properly. They think that everything, when you put down, it is a flat, nice thin film. It is not. It could be any one of these structures. Okay. This is to emphasize again, because this is one area which I think almost 15, 20 years, the whole world was absorbed in. And there was, people naturally wanted silicon films. And silicon film means they took silane, for example, SiH4, and they put it in a plasma. In a plasma, glow discharge plasma, it breaks up. And I wanted to emphasize that. Silicon SiH4, it breaks up into almost any little species that it can be. Like its species SiH, SiH2, SiH3, SiH4, Si2H6, and then hydrogen and hydrogen molecule, and then silicon. So your plasma, for example, consists of all this junk material that you can see here. Okay, now it's up to you. When you deposit it, you may get a whole mixture of these things. This is why silicon film was creating problem. A lot of people were studying at that time because naturally people wanted to make silicon films, particularly for electronic devices, and they realized that they were getting some material which was unusual. Unusual means in this case a very high resistivity, for example. And of course, there was amorphous silicon. So this is a discovery, major discovery, which led for almost 10, 15 years. Almost everybody in the world here was working. Just like they are working on nano today, they were working on amorphous silicon. So were we at that time. Okay. So, but the thing is, what you are getting is something very different, and I'm showing that. Okay, I'm showing here now, for example. So silicon is a very difficult material. Silicon has tetrahedral bonds. The angle between the two bonds, for example, 100 and something 9 degrees, for example. Now, if this is so, you can imagine 4 atoms have to come on a surface, and they run around to form 190 precisely, absolutely precisely. Now, imagine they have that much intelligence to do that, but you have to give them time, you have to give them mobility. So you cannot form crystalline silicon unless you give a lot of temperature, high temperature, good nice surface. They will not. Otherwise, they'll get stuck in the mud and they'll form amorphous structure, as you see in a mud. And when you form amorphous structure, naturally bonds are broken. And when the bonds are broken, then you can put any junk into it. So this was a great discovery. That amorphous silicon, of course, there was a lot of hydrogen in silane. So hydrogen got absorbed. So they produced a new material called amorphous silicon hydride with a lot of hydrogen. Okay, but it turned out that you can put in almost anything else. You can put in a lot of junk in it, and you form different materials. So I mean, I'm showing here optical absorption as a function of energy for different materials like amorphous silicon, crystalline silicon, micro. They're all different. So you can see here the thin film that you make many of these materials, you can change the band gap from anywhere from 0.8 to almost 1.2. Okay. So of course you can even go higher if you want to. Okay. This is just to show you that this is not only amorphous silicon and hydrogenated amorphous silicon. Of course, as you probably remember here, 15 years amorphous silicon solar cells reigned supreme. Everybody thought that was the energy solution for the whole world. But then it turns out they were not very stable when you go to higher efficiencies. And so new materials have taken place. One of the materials was taken place is copper indium selenide and sulfide, in which we worked quite a bit of it. In fact, one of our students has a factory in Switzerland making something like 10 megawatts of silicon amorphous thin film copper indium selenide solar cells. Okay, this is just to show you what happens here. You see, we have given a material. I've given here absorption coefficient versus energy from different sources. A 3-source material from a lab in USA, thin film lab from here, nanocrystalline, another material from somebody else, and so on. Just to show you what really takes place. The material that you produce varies in quality and optical properties drastically. This is to emphasize to the students what happens here. So you can say the band gap is changing, the whole absorption coefficient is changing. That depends very much on whether you are 3-source or 2-source material, or you are screen printing it, you are flash evaporating it, and so on and so on. Okay. Another material that we have pioneered, and indeed, unfortunately, we never patented it. This is a CBD process, chemical bond deposition process for cadmium sulfide. As you know, cadmium sulfide is used in many materials today, particularly solar cells today. Cadmium sulfide, cadmium telluride solar cells, cadmium sulfide with copper indium selenide solar cells, with a whole variety of other materials there. Okay. Now, what I wanted to show you was that deposition of cadmium sulfide by chemical process was known for a long time. Thiourea, you take thiourea and ammonia and reaction, and you get something called cadmium sulfide. But people did not realize that what they were getting had various properties. So one of our PhD student thesis in 1980 was to know what is going on here. And the lady recognized that something else is going on, and we had become electrochemists to understand that. It depends very much on the pH value of ammonia or of cadmium, and this made a very major difference. So depending on what the values were, you could get a powder, you could get cadmium sulfide, which is hexagonal, or you could get a cubic or a mixture of them. So you see, this is a lot of work, 3 years of work here. Unfortunately, we did not patent it. There are people in the world who are nice to us, okay? They call it Chopra process, CBD process. But this is probably most important contribution coming from our thin film lab to the world here. Because almost all processes that use thin films of cadmium sulfide for solar cells, they use this CBD process today, okay? Okay, so now afterwards, obviously, people became more curious, and they had more technology, they had more powerful sputtering systems and powerful electron gun systems and so on. So what they found is, this is taking carbon. No, carbon, when you deposit carbon, really goes in a graphitic form. Normally, it tries to go in a graphic flat, but then there are a lot of stresses involved in it. And then it is the stresses which that then make them more like a cube or a football. This is just to emphasize that, obviously there was a lot of excitement when you get football structures and nanotubes and so on. It really starts as a graphene as a one monolayer, 2 layers, for example, in a flat form. It is that which converts itself because of the bond being not satisfied properly. They roll around, try to minimize the energy. And this is what the formation is. So, and this is exactly what happens here. So carbon, of course, is the most beautiful material. It has a lot of polymorph, and that depends on what you do, how you do it. then amorphous carbon, diamond-like carbon, graphene, graphite, diamond, fullerene, carbon nanotubes, and so on. So these are the allotropes of carbon. And of course, it's a very powerful. So now let me, particularly for the young people, tell them something very important here. Now, of course, we use another language now, the quantum materials, we quantum dots and quantum nanoparticles. So in that language, it is called zero-dimensional. If the particles have all the three dimensions are very small and they show quantum behavior, they're nanoparticles. So they're called nanoparticles. They are zero-dimensional. Okay, physicists like to call them zero-dimensional. Of course, if they make wires, nanotubes, and so on, there's a one-dimensional. Thin films obviously are two-dimensional. That is the thickness side is nano, and the other side, XY, for example, the Z direction is nano and XY is but something that people are never, our students are never taught, that is because our universities, even IITs, don't teach what is called surface science and technology. Surface science and technology normally is left to the chemists to teach. It's very unfortunate because there's a lot of our today electronics depend on surface technologies today. What I want to show at the nanostructure surface and green boundaries is that on the surface is different from the bulk because the atoms on the surface do not have their bonds satisfied. Their bonds are dangling because they're left in vacuum or air. There is no atom beyond that which will couple with them. So therefore, the surface of any material, doesn't matter biological or otherwise, all materials on the surface is nanostructured. That is, the few atom layer, 2 to 3 or 4, depending on the material, they are nanostructured. They have a different structure. They are very, this is probably the most natural way of making nanomaterials, if you want to say that. At the same time, let me tell you something else, which a lot of people don't teach. That is when the atom, when we make any material, they come together, form grain boundaries. Okay, everybody talks about grain boundaries. But grain boundaries are normally, generally speaking, are nano. The grain boundaries are few atoms, maybe tens of atoms at the most. Okay, they are nano. So you see, naturally, when we put atoms together and make crystals, and the crystal come together, they form nano boundaries. The grain boundaries are nanomaterials. So this is interesting, and we have used the property of nanomaterials in making a device. In fact, has gone to industry, for example, a varistor. We have made a zinc oxide varistor, which depends on the properties of that nanomaterial between grains. In fact, that is the material where it's a pure zinc oxide and it's a very high resistivity, for example, and you can make a varistor out of that thing. Similarly, all materials on the surface are thin film, they are nanostructured, and that's why we have a lot of properties of materials, particularly chemical engineers recognize that, and they can be either used or they can be abused if you want to, or they will be mischievous in the properties of many devices that you make. Okay. So this is how we will define them. Thin film, as I said, 2D material. Thick film. See, this is the bottom-up process. Thin films are always bottom-up process. But thick film is another process where you thin down a material, you print it or spray it, for example. But you know, technology people or industry people don't care about whether you call it a thin film. They only call films or coating. They use the word coating. Okay. So nanomaterial can be 0-dimensional, 1-dimensional, 2-dimensional. And remember, I want to emphasize the surface of any material, living, non-living, is nano. Now that I think when you go and teach students here, you're going to shock anybody. Is surface. My hand has on the surface is nano. And that's why it behaves in many different ways. For example, if I put, there's a lot of sodium on my hand, on your hand also. The sodium is ionized because of the structure that way. So the sodium ions are running around. That's why when you go to a very clean lab, they put gloves on it because they don't want you to touch anything because that has a lot of sodium in it. Okay. So now the properties, of course, all properties change. I'm not going to go and give a lecture, but just to show you. Thermodynamic surface energy changes, for example, solubility change, phase diagram change, physical properties change, surface area, chemical activity changes, electrical properties change, mean free path changes, quantum size effect changes, optical properties change, optical constant change, and so on. The magnetic properties change, and this is where we got into the spintronics, for example. Similarly, mechanical properties change, the strength of material, elasticity, and hardness, tribology. For example, all these properties like tribology, hardness, the strength, for example, they are strongly dependent on the surface. So the mechanical, that's why mechanical people teach surface science. They have to teach it because a lot of things depend on that. So it's a very great challenge that size dependent changes of physical, chemical, biochemical properties. They have to be looked at not just in the electron microscope for publishing papers, but from the point of view of fundamental insights. Okay, so these are now. I will now illustrate with some of the examples and applications, for example. So there are a whole variety of decorative applications. And of course, all of us wake up in the morning and look in the mirror, and there's a thin film of silver or equivalent material. Okay, so there are decorative coatings. A lot of ladies use decorative coatings on their and the jewelry, for example. Okay, but most important, so you wake up in the morning. Men wake up in the morning, shave, and they use a blade. That blade is coated. Incidentally, Thin Film Lab is the first one in the world which did that job for a private company, for example, 7 o'clock company. We coated their blade because they were unhappy. They were running around. Their blades don't last more than one shave. They went abroad, and the people in France told them, "Why are you coming here? Go back to India." And there's a man named Chopra who has just gone back. He is the only one who knows what sputtering can be done. So we did this sputtering. So all your blades are coated today, and that's the same technology. Again, we were unfortunately in IIT at that time. There was no system. There was no patenting, and so on. So we should have patented that. Okay. So this is a technology which is used in a lot of hardware resistant, typological coatings, machine tools, razor blades. Optics, of course, cannot do without thin films. Okay, interference coating, selective coating, hologram, laser mirrors, photonics, quantum metrology. Today, all these standards of current, voltage, resistance, for example, are quantum, and they are all thin film based. Okay, magnetic memories, of course, you are familiar with. Spintronic now coming in, ferroelectric memories, and integrated circuits. They all depend on this thin film. Whole variety of sensors, gas sensors, pressure sensors, flow sensors, temperature sensors. They're all based on thin film technology today. And of course, energy conversion, solar cells, so on, catalysis, and so on. So there's a whole range of these properties. Okay. Now I'll go a little more detailed in surface end because that has been our very strong area for a lot of our PhD students have done that, and some have even set up the industries, for example. We have a dozen industries. Our students have set up a dozen industries in the world today. Super hard coating, for example, that also is a problem which came to us from Pune. The people who are manufacturing machine tools, for example, drills. Drills don't last very long. You keep drilling, and afterward, drill wears out, and so it messes up the holes. Okay? So they want to make a strong drill which can drill, say, 100,000 times, for example, without default deformation. So it needs, and they came to us. They said, help us there, and we helped them with carbides, tungsten carbide, chromium nitride, and you could increase the lifetime of many of these coatings. So these are tribological coatings. How do we change the friction, for example? We can change the friction. Okay, the other area that has become very important, was important, and today is important because of solar cells today, and now some companies have come up with coatings which are hydrophilic or hydrophobic. See, solar cells outside when rain comes, and then the dust comes and settles on that thing. That's a hell of a job, and you need coating. So finally, I think people have put a lot of effort in. Now you got coatings which are hydrophobic. So coatings of new solar cells will come where they will clean themselves. So just like the natural processes. So there are decorative coatings, stealth coatings. The aeroplane industry uses it, defense uses it. Barrier coatings, again thermal barriers. You can heat a material and you can have a very thin layer in between. You won't feel the temperature. So essentially, its emissivity is controlled, and so you can bring your hand up to 800,000 degrees centigrade heated surface today within literally several millimeters, and you won't feel it. Okay. And then optically surface selective coating, which will absorb light but will not re-radiate, for example. Okay, it will become hot, but it will not radiate. Okay. So these are optical selective coatings. Okay. So just to give you some examples, I mean, I'm taking from our student now. He's an NAL, one of the students. He's done a great job. So you can see whatever drill they do, titanium coated, titanium, aluminum nitride, silicon nitride, and so on. So there are a variety of tools here which are today done. And of course, you can do beautiful color coating also. The bangles, the ladies love it. That's all thin film. Incidentally, coating bangles with thin film was also done by our MTech students here. They set up industry in Firozabad and near UP. And of course, that town has become a bangle making town. So all sort of interference colors were created by our students there. Okay. So I said hydrophobic because I think this has become important today. And people naturally were curious, how does nature do something? How does, for example, nature also creates very beautiful things for us. So water doves and lotus. Lotus is well known. The lotus does not, you cannot put, if you put water in it, it does not get wet. And if there's dirt on it, the water that you put on it will take away the dirt. So it cleanses by itself. So lotus, and we obviously love it. And of course, the Indians also maybe respect it also from religious point of view, lotus leaves. Well, how do you copy that structure? This is a beautiful double layer, double roughness structure. And it turns out very nicely. You can do a zinc oxide. You can deposit zinc oxide so that it is very rough. I mean, as I said, you can make it very smooth if you want. You can make it very rough, like pillars, for example. So it's shown here, nano roughness. You can make a nano roughness, and lo and behold, this becomes a beautiful structure for solar cells now to be coated. Actually, this is not as simple as that. There are a number of things that have gone in. And now I think when you buy the new solar cell panels, hopefully they will come coated with this material, zinc oxide. You can see the contact angle of zinc oxide is 158 degrees, whereas Teflon is 152 degrees. And I think the nature's lotus leaves have only 45 to 150, something like that. Okay. So we can do better than nature with zinc oxide, rough zinc oxide. So you see, we can change the structure of zinc oxide. We can make it a very nice smooth film. We can make a very rough, nano rough, for example. This just to emphasize where this technology goes in so many areas, like thermal barrier coatings, for example, and these are turbines, aircraft actually uses a lot of thin film technology. But thermal barriers are used in a lot of places, oxidation resistance, thermal barriers, nanostructure ceramic coatings to increase their strength. So mechanical strength is important, thermal conductivity is important, and their erosion is important, their oxidation is important. So this is, I think, probably the maximum contribution of thin films is in the thermal barrier coating for the aeroplanes, for example. Okay. So energy, of course, you have selective coating, optical selective coating, which absorb radiation, become hot, but they don't re-radiate. And mind you, this is the principle we have to understand when we teach our physics, first year physics here. We always teach good absorbers are good emitters. Okay, fine, but we don't say anything more than that, unfortunately. That is because absorption process and emission process can be separated out. They are in different wavelengths, for example. So that's exactly what thin film technology does. It gives a material which will absorb but not re-emit, for example. So the emissivity is very poor in infrared. So optically selective coating, in fact, this is an area where our students have done a lot of work for PhDs and thereafter in this industry now. So these are so-called thermally selective coatings. Okay. I'll show an example thereof. Thin film solar cells, of course, we do a lot of things. Okay, we have at least one major industry which is using copper indium selenide solar cells. Okay, which is manufacturing copper indium selenide solar cells. So there are nano powders for hydrogen, thermoelectrics, for example, fuel cells, thermal storage, thermal barriers, LEDs, and of course LEDs depend very heavily on thin film technology. Okay. This is again to give you example from NAL. Again, our student here has done that. Okay, just to show you to what extreme level can we go. In fact, he's not happy. Nobody's happy. They want to go. For example, if you have titanium aluminum nitride on titanium aluminum oxynitride on silicon nitride. Now you can see here how all the three layers, they have their own functions. Okay, so you can absorb 95% of the spectrum of solar spectrum in it. And it goes to temperatures up to 600 degrees centigrade. But at that temperature, you would think that it will start radiating a lot. Well, it does not allow radiation to go. 0.07. Emissivity is 0.07. So you can see that today we have reached that, but people are not satisfied. They want to go to 800 to 1000 degrees if you can. and I'm sure someday it will be possible. But they don't require a number of multi-layers, for example. They do different ones. So this NAL people have done the patents here, but I think technology is moving slowly towards higher temperature, 800 degrees centigrade. Then, of course, like the solar cell, this will also become a very major area for using solar energy, for example, to convert to solar thermal and electricity, for example. So there are a number of such examples there. Of course, the solar cell 3 today, amorphous silicon, of course, is out now. The other two cells are still in surviving and thriving at the moment, okay. And the copper indium selenide and cadmium telluride solar cell. All I will say is that, okay, 20% efficiency is obtained. Our student who is in Switzerland, settled there now, has a company. He makes it flexible. I think his specialization is that it's a flexible solar cell. You can wrap it around wherever you want to, and so it is today a very major industry today, particularly for defense people, because they want these solar cells on the heads of their soldiers, so they can communicate with the power that they get from that communication network. They can be in touch. All the soldiers can be. So it's a very important area today. And of course, cadmium telluride, cadmium sulfide is also doing fine, but not that fine. I think copper indium selenide is running supreme today. But there are three cells that really are important today. One is, of course, the silicon. Silicon going to 25% efficiency already, and it will probably continue for a long time before thin films take over completely from it. The thin films, of course, is, as I said, CIGS, copper indium selenide, and the cadmium telluride source, and the other one which has come in and is making all sort of news today, still not in production anywhere, not on a large scale, perovskite. Okay, that's a larger area today. Okay, so they also have gone to 24% efficiency. Perovskites have gone to 21, 22%. I'm sorry, thin film solar cells, CIGS 22%, and silicon, of course, has crossed 25% already. Okay. If you want to go to higher efficiency, because a lot of people want, particularly politicians, want to hear 40% efficiency. Unfortunately, I think some of our very top people have been saying, oh, the world has gone to 45%, 50%. Actually, you can, but you pay for it. You pay a lot for it. You can see, this is why I just wanted to show you that you have to make a multi-junction structure so that it can absorb different parts of the spectrum, solar spectrum, to get you 40% efficiency. So obviously, this is the sort of thing very, very unique, very expensive, and obviously it can only be used by people who really need it badly, and that's probably the military, Air Force people. Okay, just to show you that, I won't go into details, but you can see here gallium arsenide, and then aluminum oxide, and then you go to gallium indium phosphide. So it's not a simple process. So the multi-junction thin film source can achieve and have achieved 40% efficiency. Okay, and of course this is the top of the thing. Okay. The fellows who I think they deserve the Nobel Prize, making a blue LED. So and LED could not be made blue because of the materials involved here, and they had to play around with quantum wells, indium gallium nitride quantum well, and I will not discuss in more details here, but you can see it's a very complicated structure they created, and they took many years of this research here. On the sapphire, you have gallium nitride buffer layer, and then you have a whole variety of different graded band gap solar cells. Okay, so this is how they achieved very high efficiency, and of course now, and they benefited from a very famous scientist, Christian Huygens, and who predicted in 1673. Well, you want a white light, then yellow and blue might be sufficient. You know, some people thought you need a green, blue, and yellow, but he said yellow and blue might, and that's exactly what these fellows have done. And they given a blue LED first time, and of course they deserved that. They got a Nobel Prize in 2014. Okay, and this is all thin film technology. Okay, well, thin film technology, of course, goes now today in biological materials, okay, biological application, a lot of it. Okay, this just to show you what happens here. The proteins, for example, are look at their size. They are only few nanomillimeters. Similarly, viruses they are also in tens of nanometers. Okay? Our bacteria are also very small. So if you make a surface rough surface by thin film technology, then you can catch these proteins. You can catch these viruses, and that's exactly what people are doing today. Okay, so you create a rough structure and you catch them, and then you go to the Raman and you can detect whatever the material is. Okay, so I think, oh yeah, okay, there is this. So I think I should be showing that. Okay. All right, let me show that first. Okay, so you can see here, this is one of our colleagues who worked at NPL. He worked with Thin Film Lab also for a short time. So what did he do? He took gold nanoparticles. Instead of making a thin film gold, he stopped at the early stage and made nanoparticles. And then bring it in contact with sulfur. They make a gold thiol bond. And the thiol bond is the one which will attract the viruses like HIV, rhinoviruses, and so on. And then, of course, you go to Raman and you can detect. And so this has become a very major tool today in biotechnology today. And you can make biosensors. You can detect a whole variety of viruses, for example. On the right side, I show you here sputter deposited biocompatible titanium coating. This is one of our students who has a company in Australia. You see, you use a lot of these things, for example, in your teeth. Those who can afford it, you know, and holding your teeth when your teeth are broken or you have a new teeth, they hold it down with a screw, for example. No, the screw has to be obviously insensitive to all the things in the mouth. Okay. So you can coat them with the titanium coating, for example. He is doing that on a commercial scale. And so this is another way. Of course, wherever you require any broken bones and so on, I think you connect them, then this technology is very important. Okay, so the quantum standards, of course, is another area that we should be teaching. Today, current voltage frequency standards are no more the old-fashioned standards. They are based on quantum phenomena, quantum Hall effect, Josephson effect, and so on. So and very high accuracy, 1 part in 100 billion, for example. So this is a very important area. Unfortunately, we don't do much of it. We only buy quantum standards from outside, or from National Bureau of Standards. We purchase them, for our NPL has them, for example. But these are today based on the current voltage and frequency. I will not go into the mechanism that goes in, or what are the various effects, for example, Josephson effect and so on, quantum Hall effect. So just to show you that the whole thing is taken seriously worldwide, and obviously has won a lot of Nobel Prizes based on thin films. Okay, so like for example, tunneling junctions. For example, the one I've showed, which resulted in all the technologies that I've talked about. Gaver, Isaki, and Josephson, they got a Nobel Prize in 1973. Tunneling phenomenon, superconducting junction, Clissing quantized Hall effect, which is responsible for that quantum standard today, and he got a Nobel in '85. Then, of course, the STM AFM people, they also were using these similar techniques here for making their devices. Okay, so they got a Nobel. High temperature superconductor thin film, Nobel. Conducting polymers, for example, Nobel 2000 Eager, Dearman. You know, I started my work in Thin Film Lab in 1970 on conducting polymers, because in my book I say, if somebody has read it properly at the end, that the future is in conducting polymers. So I gave that problem. Unfortunately, we were physicists, not good chemists, and we made semi-conducting or more or less semi-metallic conducting polymer, but we could not make conducting polymer. But anyway, our chemistry was bad at that time. Then the GMR, joint magnetoresistance, colossal magnetoresistance, got a Nobel Prize. These are all thin film based. Graphene is of course thin film also. Some people will call it nano, but it is really thin film. Okay. Quasi-crystalline thin film structures, again, 2011 Nobel Prize. Gallium nitride blue lead, that's a Nobel Prize. Okay, so you can see how many Nobel Prizes come in an area of thin film. So essentially, as I said, we started from unpredictable thin. We didn't know at that time what is going on, why these materials bend thin, make them, why do they behave differently. And indeed, I remember, because I was in USA going to conferences, and we would present our data, and there would be a lot of hue and cry, shouting at each other. Oh, I got this result from my cadmium sulfide. You got different results. Why? So the result was that we did not know at those days what is depletion was. And this is our major contribution. Many of us, many other scientists have done it, and our group has done too. In fact, much of this work was done by me when I was in the US, nuclear growth. So what I want to emphasize is that nuclear growth is important for them to understand that. And of course, now today it has become a $1 trillion industry application there. Of course, now everything we make very small, we call it nano anyway. So new phenomena, new materials, new development, and nano analytical techniques are there to help them. So it's a low dimensional nano state method of nanoscience and nanotechnology. And of course, this has got a lot of other issues that I will not talk. But from thin films, we have come to know so-called low-dimensional nanomaterials. And thin films, obviously, are the kingpin of this whole thing. In fact, most applications today still are thin films applications. Okay. So, what is future then? What is the future of this? Well, obviously, everybody knows now what is called move. We have reached already making transistors with almost 8 to 10, less than 10 electrons we're using to make a transistor today. And that's very tricky. I mean, you're using only 10 electrons, okay. And how do you go below that thing? So we have already hit the Moore limit long time ago, and now they want to go beyond that. So they go single electronics, molecular electronics, quantum computers, they are coming in, photonic chips. But they will all still depend on the techniques that I mentioned today, ultimately. So optical electronic neural networks, transparent, flexible, variable electronics, terahertz electronics, flexible thin film solar energy conversion, thin film LEDs, OLEDs, of course they're coming in, thin film ionics. So this is another area. Now, we are not chemists and chemical engineers, so we don't talk of ions. We think ions are so heavy, how will they produce fast electrons? This is not correct. And in fact, this may very well be one of the major areas to develop now, thin film ionics. Because reason is, after all, our brain, human being, our brains is working on ionics. It is the ions that are doing it, not the electrons. Okay. Okay. So thin film batteries, biosensors. So in a way, what is happening is that not any one of the single subjects, you have to integrate that. Integrated photonics, integrate with it plasmonics, spintronics, and bionics. So this is the future of this. Okay. So I hope is it okay? And time-wise, all right. I'll take 2 more minutes. Okay. So there are certain myths that need to be taught but are not taught, and I want to emphasize that. For example, everybody thinks when you deposit a material from multi-component, you always think that thin film has the same composition. It's not so, because it depends very much on how many atoms are coming, how many are sticking, how many are reacting, and so. And then people say it takes place layer by layer. Everybody talks about today 1 nanometer, 2 nanometer, and they don't understand, is it layer by layer or not? Very, very rarely, under very, very difficult. Silicon can be done. If you have very high temperature, you can go layer by layer. Films are continuous at anything. They think the film, when you put it away, it's continuous. Not so. They are atomically smooth. Not so. Their properties are not, they say extrinsic properties due to structure are not emergent. In fact, they are dominated by these properties of the surface, for example. Films of material deposits by different techniques have similar properties. Absolutely no. So you do chemical deposition or sputter deposition or evaporation, they are entirely different. Even material like gold, which is a very subdued sort of material which will behave very nicely, will give you different properties under different conditions. Okay. So epitaxy, they say, occurs when lattice constant film and substrate match. No, not at all. In fact, in most cases, there's a lot of mismatch, but then you control how the epitaxial takes place. Okay. So epitaxial films, they say, are single crystals. A lot of them call them single. It's not so. So thin films are generally nanostructured. Epitaxial films are generally low-angle grain boundary. In fact, the largest single crystal in an epitaxial film is in silicon over 100 microns. You cannot make any more than that. Nobody has ever made a single crystal epitaxial film over a large area. Nobody has done it. Okay. All right. So concluded remarks is that thin film technologies have enabled us to create 0, 1, and 2-dimensional materials in various shapes and sizes. And thin film technology is the mother of nanotechnology. Thin films provide the most stable and useful form, and that's why they are used in the industry today, the $1 trillion industry, manufacturing industry. Multi-dimensional, multifunctional, low-dimensional designer materials have opened new frontiers of cross-disciplinary, physical, chemical, metallurgical, biological, and medical sciences. So they are playing a very important role. They have played in all our revolutions, like tech revolutions, have PC revolution, internet revolution, mobile revolution, digital revolution, LED revolution. And this is all due to thin films. Unfortunately, the word thin film is not very attractive. Nobody wants the word thin films, okay? Except the ladies, they would like to be thin film, thin, okay? But thin films is not. So everybody loves the word nano. That's okay. It's a very fancy name, but beautiful thin films are the most beautiful thin nano materials, okay? So they are smart. There's no doubt about that, and they are bountiful, okay? So finally, let me also mention our major contribution. And I must say that we were ignorant people because our IIT was being, created at that time. Lab was created from nothing, and we did not patent. And unfortunately, we had that patented it. I think all these major things that our contribution should have become major industrial products. Chromium coated 7 o'clock razor blade, which we did for a private company in 1970, and they paid 30,000 rupees our fee for showing them how to deposit chromium on this. Okay, that's in 1970. This is equal to 30 lakhs today. Thin film cadmium sulfide solution coat process. Everybody in the world uses it, and that's our process. Conducting zinc oxide. When we made conducting zinc, nobody believed it. Nobody believed it in the world. I was given hell by numbers. And Japanese 3 scientists arrived at midnight in my lab. My lab was always open, and they knew that. So they came directly from the airport to the. Similarly, Germans came to our lab at midnight, and they wanted to see the zinc oxide films. Okay, and we did give them, and then they invited me to come and give lectures and zinc oxide. So similarly, our Professor C.N. Rao, he said, nonsense. Zinc oxide can never be conducting. It's a very beautiful, wonderful insulator. And so he invited me, and I went there with samples and so on. Even after lectures, he said, it's not. I said, this is your zinc oxide film. Keep it in your pocket and go and measure in your lab. And then thereafter, he started writing papers on zinc oxide. Okay. Joint photoconduction effect in chalcognine film is one of our major contributions. Zinc oxide based varistor we contributed to a company in Shanghai. They are making these varistors. Iron beam vacuum sputtering process is our process here, and is very important. Okay. So this is really all I have to say today, and I hope I have been heard. Is that okay? Hello. Hello.
Yes, sir.
Oh, it was clear. All right. Oh. Andy. Okay. Clear?
Sir, can we open the discussions?
Okay. Up to you.
Okay. If anybody has any question to ask, kindly type it into the box.
Hey, Baba, your voice.
Sir, one question that.
Hello, I'm Dr. Shaktivel from Sarfoji Government College, Tanjavur, Tamil Nadu. I am very thankful to Professor Jayakrishnan for arranging such a wonderful lecture. I met Professor K.L. Chopra in the year 1996 when I was a research scholar in the Department of Physics, Bharatiyar University, Coimbatore. Professor Narayan Das and Professor Mangalaraj. Mangalaraj is my guide. And at that time, I met Professor K.L. Chopra. And I have learned a lot of things during the time of conference. And once again, I am very thankful to Professor K.L. Chopra. Thank you, sir. Thank you very much.
Okay,
thank
my pleasure. Okay, always. Hani, so you want to ask, somebody wants to ask something or what? Okay?
Yes, sir. One question.
Yeah.
Sir, question is, what materials can be used for diamond-like coatings, and which is the best technique for that?
Oh my God, you are asking. Diamond, God knows how many people have done. Obviously, they deposit naturally from any carbon-based material, which has a high vapor pressure, because it will be easier to evaporate that and then deposit it. So any carbon-bearing material should be okay. But I think there are a lot of materials. I don't think there's not one single material. You are to. There's a lot of literature on diamond coatings. Okay, so please see that. All right. I mean, obviously, you don't use charcoal on that. If it's a chemical process, you take a carbon-based material in a vapor form, for example. carbon tetrafluoride, for example. You can do that, okay, if you want to. So carbon chlorides, carbon, so I think people have used a whole variety of different materials. Yes. Okay. Haji. All right. Everybody is happy, satisfied. Okay. ठीक है. That's it. Doesn't the material coated on a single? Okay. There was a question here. Somebody had a question on. You have removed it already.
So the question is, doesn't the material coated on a surface degrade fast? What is to be done to avoid that?
No, let me hear it again. Does it? If it's coated on
surface degrade fast.
It was on the screen already. If you have removed it.
So it is there in the chat box.
Okay. All right. Repeat it. Slowly. The old man. Well, you know, very old. Okay, so you have to speak slowly. That's what. And okay.
So the question is, doesn't the matter coated on a surface degrade fast?
Why do they degrade?
What is to be done? I think the question refers to the material getting peeled off from the substrate.
I'm not able to follow, but anyway. Thin films, as I said, surface of any material, not only thin films, surface of my hand has its own problem. That's why we get sick very easily, because surface is a very active material. Any surface is a very active material simply because the atoms on the surface are not bonded properly. Their dangling bonds are very hungry to get anything trapped in it. So this is why when you bring any material, it's very easy to become dirty, very easy to contaminate with biological material and so on. So any surface is in a way very active, very reactive, that you must understand. So this is why all the technology, electron technology, you have to passivate all these devices. So you passivate by device like silicon nitride. Silicon nitride has a beautiful thing here, okay? So their bonds get bent. Their bonds bend on the surface, and so they keep the surface happy. So all silicon devices, for example, they have to be coated with something like silicon nitride or something like that. Okay, all right. Is that okay? Anji, does that satisfy the?
Sir, can you please tell me the best method to make thin films out of nanocolloidal solutions?
Nanocolloidal solution.
Yeah, like we can use spin coating or spray pyrolysis, etc. So
yeah, okay. You can use spray pyrolysis. Okay. You can do spray pyrolysis. You can do even electrolysis. If you do it very rapid electrolysis, for example, it will form nanoparticles. So anything done rapidly, whether you by physical evaporation or electrochemical evaporation, if you do very rapidly, that means you put atoms so fast that they don't have a time to rearrange and become gentle and normal. Okay. So when they don't become normal, they make clusters. That's easy. It's okay. So this is to put in material atoms or molecules very rapidly, very large number. Okay. And of course, if they are tetrahedral coordination like silicon has it, a diamond has it, then they find difficult. The atoms cannot run around to make 104 degrees. So it's not easy. But amazing how clever the atoms are. If you give them enough time, enough temperature, they can make a diamond by running around and forming their heart. So you will ask this question, and that you should ask the God Almighty. How do the atoms know how to make exactly 104 degrees, 104.9 degrees precisely? They do that. Okay. So these are attractive. Yeah. Okay. Fine. All right. Anji. Okay.
yes.
Does anyone teach thin films? Okay. Anybody is teaching in this course?
No,
thin film science is being taught to MSc students.
Sir, yeah, which technique is suitable for? I think it's the same. Now for preparing QD solar cell, please give me some suitable perovskite.
No, your voice is coming in a broken way. Okay, but anyway, you see, all techniques have their advantages and disadvantages. No technique is perfect. No technique is perfect. And it depends on what you want to make use of. For example, you want to use the energy, naturally you go to sputtering process. There's a lot of energy. Okay. So you can make much stronger structures, much more coherent structures, but obviously the energy has been pumped into the atoms when they are in ion form. Okay. Simple electrolysis is okay too. I mean, I think it depends really on what material and what you want the material to do. So you want an epitaxial film, naturally you want a high temperature substrate, so it is better to go very slowly, put atom by atom slowly, and that's what the epitaxy people do that. Okay, MBE is essentially that. MBE is a very slow process of depositing atoms at high temperature under ultra high vacuum conditions. And that's exactly all electronic people depend on that. Okay. But chemical people want to synthesis of materials, very large number of materials, for example, on a surface, then they will do chemical processing. So I have students here and NML, National Metallurgical Lab here. She does a lot of things on coating, hard coatings on surfaces so that, they don't corrode or they have lesser friction and so on. So it depends on applications, which technique you use. Each technique has its own merits and demerits. Okay. 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 Fine.
Okay. If there are no more questions, next I would like to invite Dr. Deepa KG, Assistant Professor, Department of Physics, University of Kerala, to give the vote of thanks.
Okay. All right.
Good afternoon, everyone. Honorable Professor K.L. Chopra, Honorable Vice Chancellor Professor Mahadevan Pillai, respected faculty members and dear students. I feel that it's a considerable privilege in having the opportunity to propose the vote of thanks on such a great occasion, which will be carved in golden letters in the history of the department. A day which I'm sure will be cherished by all of us who are here for years. The plenary talk by Professor K.L. Chopra was taken us through the last 4 decades of development as great insight about versatile application of thin film technology in our daily life, ranging from razor blade to gaming. I'm sure that the campus attendees, including faculties, researchers, and students, will greatly be benefited from this talk. Sir, in this occasion, I feel proud to remember and recollect my PhD days, during which your book on thin film solar cell was of great help in understanding thin film physics. Our group was specifically working on developing thin film for solar cell applications.
Okay, great.
So now let me come to my duty now. On behalf of Department of Physics, University of Kerala, and also personally, I extend a very special thanks to Padmasree Professor K.L. Chopra for gracing this occasion with their support and for sharing with us his rich experience and knowledge today. Thank you very much, sir.
Very nice. I see more, I think it's going 50% ladies in the Department of Physics. Is it faculty? Looks that way. Is it?
Sorry, sir.
How many ladies are faculty members of Physics Department?
Yeah, now we have 4.
4 out of 10. 10 out of 10.
Out of 10.
Very good. You're doing well then. Okay. Keep the men under control. Okay. That's okay. All right. Okay. But remember here, please teach properly. Whatever you're teaching here, I think this is not only you, it's even happening in IITs. Okay. So they take books and continue with that thing. And everything is taken as if perfect. Nothing in whatever has been done in the world today in physics, there's something always lacking. And I think the best teaching is when you point out whatever technique, whatever technology, whatever physics behind it, there are question marks. I think the question marks, when you raise it, only then you can understand physics. Okay. For example, surface. You are not the only one. I've given lectures in IIT Jammu, for example, and I asked them, do you understand because everybody thinks the surface is fine, everybody is like any other material. Surface is the most important thin film naturally available to you. And it is that property which controls friction, it controls the absorption, the emissivity, the electrical chemical reaction, and so on. So, and that's why physics people should also teach that. Surface science and technology is taught to all the scientists and engineers in American university system. It is taught. But we don't teach that because we think as if this is a part of chemistry. This is not so. And it's very simple to explain. Okay, anything sitting on a surface on atom, the atoms are not happy. The bonds are not satisfied. They're dangling. And so that's why they misbehave. That's why friction takes place. This is why corrosion takes place. Okay, this is why, so and that's a very important, very naturally given thin film to you. It's a thin film also. A dangling bond. Okay. Anji, I think we done enough now. Is that right, JK?
Yes, sir.
Yes, sir.
All right. Thank you very much. So I can switch down now. Okay.
Okay, sir. Thanks a lot.
All the best to your Department of Physics. Jubilee. Wish you a very happy future. And do keep in mind, it's not a question of teaching. It's not a question of teaching is much hard. Large amount of teaching does not help. I would rather have a small amount of teaching, but much more understandable teaching. Why do we teach all that physics? I think that's more important to teach. We keep on teaching relativity, we teach on this, but we don't tell them why. Why are we so concerned about relativity? And I asked this question because many universities now are cut down, and they measure velocity of light. I'm sure your students also measure the velocity of light, right? What different wavelengths? Or yes, you don't care. Okay, but why don't you ask them to measure different wavelengths and then ask them why are we doing it? Why are we doing it? What is so fundamental about it? That's essentially the essence of one of the essence of relativity. So the velocity of light is independent of the wavelength. Very unusual. Very unusual. It's independent of the wavelength. It's independent of the color. So what is the consequences? This is why Einstein was better, because it's a good thing he was a mechanic in his workshop in his home. When he learned all these things, he said, "Ye kya ho raha hai? Why is the energy wavelength of blue light, green light the same? Where's the problem?" That's okay. I leave that to you. So now that's a very simple thing. Is velocity of light independent of the wavelength? Well, tell the students here, and then they will start wondering why is it so? That's okay. So that's where teaching of physics is, and we don't do that. That's where the problem is. Okay. All right. All the best. All the best. Thank you very much. We wish you a
Thank you, sir.
Wonderful. Thank you, sir. The department is in gratitude to you, sir. I will personally mail you the rest.
Okay. Thank you very much. Okay. Bye.
Okay, sir. Thank you. So we officially terminate this plenary talk for this session. We will have a Golden Jubilee lecture tomorrow. So thank you one and all for participating in this event. Thank you.